Hi, I'm Christian Rossow and faculty member at the CISPA Helmholtz Center for Information Security in Germany. I will be presenting Yarix, a scalable malware intelligence framework. Yarix is joint work with my PhD student Michael Brengel. Malware analysts typically have access to large malware databases that they use on a daily basis to hunt files. As the main file hunting mechanism, they use YARA, which is a framework designed with a particular focus to search for patterns in malware sample collections. Assume an analyst is interested in spotting malware files of the so-called SCRACE family. To this end, they search which of the files contains the SCRACE typical file indicator screenblaze.exe. This is just one out of many use cases of file hunting with YARA. Others include, for example, obtaining lineage information of a certain malware family, testing new indicators of compromise, or on-demand sample sharing with other researchers. However, such sequential YARA searches do not really scale well to really large malware databases. But antivirus vendors and threat intelligence companies do have such large databases that span millions, if not even billions of malware files. Thus, our overarching research question here is, how can we use YARA efficiently in large malware databases? A simple Strawman solution would be to cache previous search results and search terms. This way, you can quickly go back to previous results and, when adding new files, flag them accordingly. The drawback, however, is that for every new query, you have to fall back to slow sequential search. In fact, though, such new queries happen regularly. For instance, when new malware families arise, or when existing signatures need to be updated, or when others ask for a change of specific malware samples. Therefore, we introduce Yarix, a generic approach that does not require any a priori knowledge of search queries. Yarix features a reverse file index that maps possible search terms to files containing them. For example, assume the following file which contains A, B, C, D, E, and so on. For each engram in this file, Yarix stores the corresponding file identifier in a per engram lookup table that we refer to as a posting list. While configurable, we find that n equals 4 is the perfect compromise between space efficiency and search performance. Yarix then processes all engrams contained in all index files and thereby builds a complete reverse index. For an arbitrary subsequent query, Yarix uses these posting lists to search for candidate files that contain the search string. To this end, we first extract engrams from the search term. For instance, when searching for ABCDE, we find two foregrams, ABCD and BCDE. We then query the respective posting lists and find that each two files, in this case gray and black and blue, contain the engrams. In this particular example, only the single file that falls into the intersection of both engram searches can be a true candidate. Yarix does not store position information about engrams, as compromised for better storage efficiency. Thus, in the last and final step, Yarix sequentially scans all candidate files to reveal the true positives and return those to the query initiator. The search terms we have used so far admittedly were straightforward and rather toy examples. In practice, threat analysts use YARA signatures that can define arbitrarily complex pattern conditions. Here's an example, which satisfies true if at least one of the two AND conditions is satisfied. We wanted Yarix to not only support simple string search, but actually to support any arbitrary YARA signature. To this end, we use abstract syntax trees to break down YARA signatures into foregrams. Yarix then searches these foregrams in its posting list and merges the individual search results to refine the minimal set of candidate files. Yarix supports many YARA features beyond plain strings. Support for hex strings is straightforward by extracting all streaks and proceed similar to plain strings. For regular expressions from the DFA, we automatically extract the plain strings that will be contained in any matching string. For search times like at least x out of the following strings, we proceed as before for strings, then count and use a cutoff threshold. Conditionals like and or are converted into candidate set intersections and unions respectively. There are many more features that Yarix supports. Please refer to the paper in the GitHub repository for full details. Whenever Yarix does not support a feature, it over-approximates search results. This way, Yarix stays sound and complete. One of the downsides of maintaining a reverse index are its storage requirements. We thus apply a few tricks to shrink the reverse index as much as possible. First, as already mentioned, we do not store n-gram offsets, and instead we store them later during the sequential scan phase. Second, instead of storing file IDs, we just store the distance to the previous file ID, that is, the predecessor in the posting list. To this end, we store IDs in a sorted manner, and store file ID offsets only. Furthermore, we use a variable length 7-bit encoding scheme to minimize the storage width of each relative file ID stored in the posting list. Finally, Yarix optionally supports an adaptive file grouping mechanism. The basic idea is to group several posting list entries into one, thereby saving storage demands at the cost of lower search performance. Without going into much details, let me briefly mention that Yarix grouping leverages the fact that Yara signatures typically search for multiple n-grams. We therefore use modular arithmetic combined with per posting list grouping such that group elements are not congruent. That is, the loss of precision that is introduced by grouping reduces significantly when intersecting multiple group search results. Details are in section 3.6 of our paper. Let me now turn to the evaluation results. We evaluated both search performance and space efficiency. We first look at search performance in terms of absolute time it requires to query common Yara signatures. To this end, we obtained 32 million malware samples and about 1,400 Yara signatures from a well-reputed repository. The following box plot shows absolute runtimes in seconds for 4 database sizes, ranging from 10,000 samples on the left to the full set of 32 million samples on the right. The blue boxes show the time required to look up the index, the red boxes the time for the sequential scan on the candidate files, and the green boxes show the total time. Let's focus on the right part of the figure. Querying 32 million files takes less than 10 seconds in most cases and a few seconds on median. A few Yara signatures in our dataset that did not allow for pre-filter heavily skew the average and can easily optimize for Yarix. Compared to sequential scans, this provides a huge speedup, which, as expected, grows with the size of the dataset at hand. For our largest dataset, Yarix is more than 5 orders of magnitude faster than sequential scans on average. This also easily illustrates that full sequential scans on larger datasets are really impractical. The speedup, of course, comes at the cost of additional storage requirements for the index. We therefore evaluated the index size relative to the sample size. Without any optimizations, as shown here, Yarix adds factor 2.8 of the sample size as overhead. Delta encoding, as shown here, reduces this overhead to factor 1.5, and even more effectively, grouping, as shown in the green line here, has an even higher effect and reduces the overhead to less than the original samples need themselves. The lower the number of groups, the less space is required, at the expense of lower search performance. As expected, using all space optimizations combined, see the purple line here, Yarix achieves the best compression result. To summarize, we presented Yarix, a Yara engine that scales to a large number of malware samples. Yarix extracts searchable terms from Yara signatures and converts them into an AST. Its underlying reverse file index helps to find candidate files effectively, speeding up over 5 orders of magnitude compared to sequential Yara skins. We released Yarix as open source tool and invite everyone for contributions. Thanks for your attention. I'm happy to take questions.